Hey everyone, welcome to this next video for EE 151 at Cal Poly. In this video, we're going to be going over Module 2 on circuit theory, signals, and measurement. So here I've got the Canvas page open, and first off, I've opened up the lecture slides or the intro slides, and we'll just kind of go through these real quick. So, first off, circuit theory, electricity is the movement of charged particles. Here I've just got a battery connected to either end of its terminals there, right? So we've got the top terminal where there's an accumulation of positive charge and a negative terminal where there's an accumulation of negative charge. And electron electrons will go from negative, right? Because they're negatively charged, so there's an accumulation of them there, and they'll want to go towards positive charge. So hopefully you've had some exposure to physics and, electricity and kind of this idea that charged particles will flow towards, their opposite. So some materials conduct electricity with low effort. Going back to here, this is kind of just an example of a copper wire. And so copper is usually a good conductor. And here are some other types of materials that are particularly good at conducting electricity. So we've got silver and seawater listed there. Some materials struggle to conduct electricity, and these are called insulators. So we got wood, rubber, and oil as examples of insulators there. And so some materials conduct electricity under some conditions. This was kind of what we explored a little bit last week with the diode, right? It only conducts electricity in one direction. Um, and so we'll get into studying some other types of these semiconductors, such as transistors. So, like I had mentioned before, charged particles can either have a positive charge or a negative charge. And like particles, will repel each other, right? So if I have two electrons or two protons, they'll want to push each other away. Whereas if we have oppositely charged particles, they'll start to attract to each other. And charged particles that are kind of stuck together will have more force, just like how objects with more mass have a stronger gravitational force. And, in the extreme case, you can think of the Earth as kind of having this overwhelming gravitational force that's pulling everything in at a kind of like a constant acceleration. Um, so these charged particles will create an electric field, kind of like how objects with mass create a gravitational field. Separating charges creates electric potential, kind of like how picking an object up off the ground creates potential energy, right? So if I were to pick up a ball off the floor, I'm moving it inside of that grav inside of that gravitational force. And so as I pick it higher and higher up off the ground, it gets more and more potential energy. So these all this electrical phenomena is kind of summarized with these Maxwell's equations, and you'll get a chance to learn about them in great detail in EE 402 and I think parts of EE 335 here at Cal Poly. Um, this course that we're, 151, we don't really assume any knowledge of calculus or differential equations, so we'll skip over this for now. But we usually approximate all of this electrical phenomena to start. So we use this lumped element model and we make a few assumptions just to make the Maxwell equations a lot easier, um, a lot more practical for these larger scale circuits that we're describing, right? Maxwell's equations is really good when circuits are, when we're looking at them really closely, but this is more of like a macroscopic scale of what's happening. All right, so we've got the change in of magnetic flux in time outside a conductor is zero, so that's the first assumption. And then the change of charge in time inside conducting elements is zero. And so that's the second assumption that we use to make Maxwell's equations easier. And, these kind of describe the lumped element model. And so all that really means is kind of like the voltages and currents are changing instantaneously, more or less, right? So wherever we are in the circuit, um, things are just happening so fast that we don't really need to consider all of these complex equations here, the Maxwell equations. And so as a result of these simplifying assumptions, we result with the Kirchhoff's current law or circuit laws. So there are two flavors of these. There's the current law and the voltage law. And so we'll get into those right here. So Kirchhoff's current law, what goes in must come out. So all of the current going into a node must equal to the current going out of a node. And so a node is just an interconnection of elements. So for example, this entire structure here is a node. I'm drawing a circle around it here on the slide. So that is considered a node because there are a bunch of elements that are interconnected there, right? Likewise, this is a node. This is another node. This is another node. So these are all separate nodes. Now, the other side of this I3 is connected to the inner node that we had circled before, so it's not necessarily a separate node. But the idea here is we have I2 and I3 going into the node. So we can write I2 plus I3, and we have I1 and I4 going out of the node, so we can subtract the sum of those guys, I1 plus I4. And in principle, this should equal zero, right? I'm adding up all of the currents going in and out of the node. What goes in must come out, so that should just equal zero. All right, so moving along, Kirchhoff's voltage law, what goes up must come down. And so here I've got an example of a voltage source with voltage V4, right? And so this is going, if I walk from node D to A, I've gone up by a voltage of V4. And typically when we think of resistors, we think of the voltage going down, just because it's absorbing power. So I'm going to call these, and so you'll notice that voltage is defined between 2 points, right? So going back to current really quickly, current is defined as going through an object, right? So it goes into the object and it comes out of the object. Um, Voltage, on the other hand, is called an across variable, right? Current is a through variable, voltage is an across variable. Across variables are defined between 2 points, much like when you measure the height of an object. Well, the height needs to be with respect to some reference point, right? So if I have a building that's, 10 feet high, um, that's usually measured with respect to the ground. And so in this case, voltage is, defined between 2 points in the circuit. We call them two nodes. And so in this case, V4, this voltage source with voltage V4 is defined between node A and D. And so we have a voltage of V4 over between those 2 points. And so just as I have defined a reference, right, of node D, I need to define a reference for all these other voltages. And so just taking a look at V1, I've defined the reference to be B, right? And so we're looking at the voltage across this resistor R1. And so that's from VA to VB. Likewise, this V4 is from VA to VD. And so, we can then go about summing all of these voltages. So if I walk in a circle, right, I'm going from D to A. I've gone up by V4 because I'm going through this positive terminal here. And now if I walk from A to B, right, I'm walking from here to here. So I've gone down by V1. So minus V1, and then I keep walking from B to C, and I've gone down V2, and now I walk from C back to D, and I've gone down a voltage of V3. And so this will all sum to 0. So hopefully that's clear. If it's not, there are a lot of good, helpful online resources that can walk you through Kirchhoff's voltage law and Kirchhoff's current law in more detail. All right, so moving on, circuit elements can be connected in series or parallel. Here on the left, I've got an example of a network of resistors connected in series. All right, and so there's only one path for current to flow. I walk into R1, I come out, and I can only go through R2. I can only go through all of these N resistors. When we have elements connected in parallel, you'll see that both of their terminals are connected between the same two nodes. So, for example, I'm going to call this the top node, and you'll see one end of each of those resistors is connected to that top node, and the other end of all of these resistors are connected to this other bottom node. And so by Kirchhoff's voltage law, what goes up must come down. So if I go up some amount of voltage through R1, I must also go down that same amount of voltage through R2 because I have a loop here, which means that the voltage across R1 is equal to the voltage across R2. Much like how in the series connection, if we examine Kirchhoff's current law, and I call this I1, well, and then if I call this I2, and if we look at this node here, I have, you know, two separate currents going into and out of that node. And so I1 minus I2 is equal to 0. Therefore, I1 is equal to I2. Um, so that's just something to note there. So this is Watt's law. Power is the product of current and voltage, and this is true from all elements, all electrical elements at least. So for a resistor, we have Ohm's law that relates voltage, current, and resistance. And so we can determine the power dissipated through a resistor using Watt's law. And you won't always see this defined as Watt's law, but some sources do. Um, so going back to this idea of power, a device can either supply or absorb power. So a device that supplies power are said to be active. We say that it's an active source. And the power is, just by definition, less than 0. So here on the left, we have an example of that. And you can see that the current, right, which is indicated by these positive moving things, is coming out of the positive end of the voltage across the element. And so when we have that case, that means that the device is supplying power, right? Current is flowing out of that device. And on the other end here, we have a passive element because it's absorbing power. And you can see on, on the contrary, there is current going into the positive terminal. And so that device is absorbing power. So this is just a summary of circuit theory. I won't go over that. And now we'll talk about signals. All right, so a signal is an object transmitted over me some media. And by media, I'm not talking about social media. I'm talking about, physical channels where we can send things. So, for example, we have electric signals, which are usually transmitted through wire, radio frequency signals, which are electromagnetic waves transmitted through air, right? And so in these cases, wire would be the media, and then air would be the media for these radio frequency signals. And so signals usually contain information, but they will always contain noise from, just a practical standpoint. Um, Signals can be classified as either analog or digital. Analog signals can be encoded to create a digital signal. So a digital signal is kind of just something that can only take a discrete number of states. For example, maybe those states are is binary, right? One and zero. So here we might encode a positive voltage as one and a negative voltage as a zero. So these digital codes, right? We've encoded something. They have some number of resolution bits. And going back to this example, this would be this would be one res bit of resolution. For n resolution bits, we have 2 to the n distinct codes, right? So again, going back to here, if I have one resolution bit, I have two distinct codes. In this case, I've made my code 1 and 0. So a 3-bit code will have 2 to the third distinct codes. So that's 8 codes, and I've enumerated them here. 0, 0, 0, 0, 0, 1. And so here on the left of this plot, we actually count up in binary to, from 0 to that last code. Um, so analog to digital converters create these digital codes, and the microcontroller doesn't exactly speak in terms of, just random floating voltages. So it needs a way to look at that voltage and say, okay, computer, here's what we're looking at. And so it does this using the analog to digital converter. So the ADC on the Uno has 10 resolution bits. I believe this is the same for the Mega as well, but we'll take a look at that later. And so that means that it can encode 2 to the 10, where, it has 2 to the 10 codes. So these 10 bits go from 0 all the way up to, all of these ones. In this case, that's 10 ones. And this is just kind of like an example of how to go about counting in case you are not familiar with counting in binary. So the principle is pretty much the same, um, but instead of carrying the 1 once we get to 9, we carry the 1 once we get to 1. Right, so I go 0, 1, carry the 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, and so on and so forth. So we also need to talk about what an operating voltage is for these ADCs. And so the operating voltage kind of gives you the range of the ADC, in terms of like kind of like the resolution steps, right? So a unit step in this case, right, we go from 0 to 1, that corresponds to a voltage of 4.9 millivolts when we get to 1. So anywhere in between 0 and 0 volts and 4.9 millivolts, this should get encoded as a 0. But once we get to 4.9 millivolts, and we're between 4.9 and 9.8, we should get a digital code returned of 2, right? 1, 0. And so once we get up to our full scale range of 5 volts, we'll get the maximum 10-bit code, which is, that 111 10 ones, which just ends up being 1023 there. All right. So these digital codes can be converted to an analog signal, and this requires a digital to analog converter. But the Arduino Mega board um, doesn't actually have a DAC. So, we'll obviously need to find a workaround. In this case, we use what's called pulse width modulation to sort of create an analog signal from a digital signal. And so we'll get into kind of like the operation of how this works. So first off, we start with a periodic signal. We kind of define what that is. So periodic signals will have an average value, um, right? Just looking at this wave here, if we multiply whatever that high value, in this case, 5 volts, by how long it's high, and so that's 50%, so like one half of whatever this duty cycle is, and then we divide by how long the period is, right? So if we suppose that the period is 2 milliseconds, we're high for half of that time, 1 millisecond, and then the high voltage is 5 volts, then you result with an average value of 2.5 volts. And, so this is just going on into more detail about how this average value is proportional to the on time. And so if we, control this periodic signals on time, we can effectively control the voltage, right? And it's not necessarily, a perfect representation of the voltage, but it does a good job, for going sufficiently fast. It creates this effective voltage, which is proportional to the on time. And so Arduino boards use this principle of pulse width modulation, and in particular, this analog write function will accomplish that, and you can read more about the analog write there. And then, here I've highlighted where these PWM pins exist, and we can leverage that capability on the Elegoo boards. But now we'll get into measurement. So we can measure many features of a signal, and we'll get to do this in the lab today. Um, but here are just some examples of measurements that you may or may have not seen before, but we have amplitude that just describes the height of a signal effectively. And then the frequency, that's just kind of like how fast it's cycling if it's periodic. And, just in the case of this sine wave that's kind of being drawn out in the middle, you can see it's pretty clearly periodic. And so it has some frequency associated with it. And frequency is usually cycles per second. Average is another useful measure of a signal typically, but sometimes it doesn't give us any useful information, right? If I were to average a sinusoid, right? Well, there's a positive half cycle and a negative half cycle. And if I average over this period, it just ends up being zero. So sometimes when we have um, signals that are bipolar like this, so they have a positive and a negative portion that kind of just cancel each other out. A more useful measure is the root mean square. And so what we do with the root mean square is we take the square root of the average of the signal squared, right? So we square this signal. And so what that in effect does is it, scales up the positive half cycle, but it scales up the negative half cycle, but it also makes it positive. And so in that way, we can actually get a more quantifiable measure of the signal with the root mean square. And so now we're just going to talk about multimeters. So multimeters give kind of like instantaneous values, and they display a single value on the screen here, and we use them to measure voltage, current, resistance. Typically, this is just a note about how to go about measuring them, right? So for measuring voltage, we want to connect our multimeter in parallel with that element. And that's just going back to kind of like Kirchhoff's voltage law, right? And how what goes up must go down. So if I create a loop by placing this voltmeter in parallel, then I can effectively measure the exact voltage drop across that element. For resistance, we connect it in parallel because, we're measuring resistance between 2 points again. Um, and so just by the physical properties of resistance, we need to connect it in parallel to measure it properly. And then to measure current, we actually need to connect this meter in series, right? And so oftentimes that involves kind of like breaking up the circuit and kind of, fiddling with this multimeter, trying to put it into the circuit, just in order to measure current. So here I've just drawn out kind of like an example. Um, First up on the left, I've got a single resistor. In the middle, I've got three resistors connected in series. And on the right, I've got three resistors connected in parallel. And in each of these cases, I've connected a multimeter to show how you would measure the total resistance of each of these networks, right? So this network of one resistor, this is how I place the multimeter. For the network of three resistors, if I wanted to measure the equivalent resistance of all three, I'd connect it like this. And then for the three in parallel, like so. This is just measuring voltage with, kind of like the same principle, but this time I've added a battery, a 1.5 volt battery to kind of like this simulation and just shown how you go about measuring voltage. And here I've gone and shown you how to measure current by placing this ammeter in series. And so one thing to note about measuring current, right, is that it doesn't really matter where in the circuit you put the ammeter, right? And so in this example on the left, I've placed the ammeter, right? So we walk out of the battery, we go into the resistor, come out of the resistor, into the ammeter, come out the ammeter, back into the battery. And in this middle example, I walk out of the battery, and then from there I go straight into the ammeter, out of the ammeter, back into my network of resistors there. Right. And so, like I said, it doesn't matter, if you come out of the ammeter, come out of the battery into the ammeter, come out of the resistor into the ammeter. All of these currents should be the same, right? Because I've got a single loop. And in this example, with the elements in parallel, you do need to be careful to make sure that all of the positive terminals of the battery, are still interconnected as well as all the negative terminals. And then I need to break up, into each of these elements in order to measure the current into each of them. And so the last thing I want to talk about briefly is oscilloscopes, and we'll dig into these more during the lab. But these just display signals over time. And so these can be a little bit more intimidating when you don't know what's going on necessarily. But there are pretty much just a few knobs and dials that we'll be using. So first off, they can be used to measure voltage and current. But current probes are usually really expensive, on the order of 500 to tens of thousands of dollars. So we'll just be measuring voltage because we only have voltage probes in our lab. And, the big two, if you come out of this class knowing nothing else, you should at least know that there's a horizontal scale and a vertical scale. And so the horizontal scale is controlled, kind of universally, but the vertical scale is controlled per channel. And so you usually have a few different channels so that you can look at different um, waveforms over time. I think in the lab, all of our scopes have two channels, which means that we can look at two voltages at any given time. Um, and so each of those channels has a vertical scale control knob, where you can adjust the vertical scaling. Um, and they usually also have automatic measurement and cursor measurement buttons, but we'll, explore those kind of like in a later lab. For now, we're just kind of getting our feet wet with these oscilloscopes here. So with that, we can go ahead and jump into the experiment. Thanks for tuning in. I'll see you guys next time.